Welcome to This Explainer. Today, we're diving straight into the hidden mechanical muscles powering our modern world. And I mean everything, from heavy industrial automation to the complex aviation systems that actually keep airplanes safely in the sky. If you've ever wondered how a pilot can effortlessly steer a massive commercial jet, or how a factory machine can lift tons of solid steel with literal millimeter precision, well, you're in the exact right place. We are going to decode the incredible science of fluid power.
Here is our roadmap for today. First, the magic of fluid power. Second, the anatomy of a system. Third, the heart, hydraulic pumps. Fourth, managing the fluid. And fifth, a showdown, hydraulics versus pneumatics.
All right, kicking things off with Section 1, the magic of fluid power.
So what exactly do we mean when we say fluid power? At its core, it's this incredibly powerful method for energy transmission. By using either pressurized liquids, which we call hydraulics, or compressed gases, known as pneumatics, within a tightly confined system, engineers can push, pull, lift, clamp, and tilt just massive loads. And what makes this so special is that absolutely no other medium combines this same degree of power, accuracy, and flexibility, all while taking up such a minimal amount of space and weight. It's pretty magical stuff.
And this macro view brilliantly illustrates how all this heavy lifting is actually done. It's basically a perfect relay race of power. Starting with an electric motor driving the system, electrical energy turns into mechanical energy. Then, the pump takes over, converting that mechanical force into hydraulic energy by pressurizing the fluid. Finally, that pressurized fluid travels over to an actuator, like a cylinder, where it's transformed right back into mechanical energy at the user end to actually move the load.
Now, you can't talk about fluid power without talking about Pascal's law. It is the absolute bedrock of hydraulic drives. Because pressure in a confined system is equal everywhere, the force that the fluid exerts is equal to the pressure multiplied by the area. So applying a very small force to a piston with a small area transfers that exact same pressure through the fluid to a much larger piston. The result? A massive upward force. It's literally mechanical leverage, but through liquid.
Let's move to Section 2, Anatomy of a System.
I like to think of this system a lot like human biology. First up, you have the reservoir, which stores the fluid, kind of like how our bodies store energy and fluids. Then you've got the pump, which acts exactly like a heart to force that fluid through the whole system. Next, we have the valves. They direct the flow and regulate pressure, just like a circulatory system. And finally, you have the actuator, which flexes its mechanical muscle to do the actual physical work.
Here we see that complete closed-loop journey mapped out. The fluid is drawn from the oil tank, pressurized by the pump, controlled by the directional valve, and then it does its work at the load. But take a look at the filter in the return line. Going back to our biology analogy, these act just like kidneys. They're absolutely vital for removing tiny contaminants like metal flakes, glass, and sand. We're talking particles as small as 1 micron. This keeps the system healthy and prevents damage to those super sensitive valves.
Now, while this anatomy gives us some incredible benefits, like massive load capacities, incredibly smooth and precise movement, and a system that's inherently self-lubricating, it's not perfect. We do have to manage a few distinct drawbacks. For one, hydraulic components require extreme precision machining, and yeah, that is not cheap. Plus, if seals fail, you get messy leaks. And since we're dealing with petroleum and synthetic oils, the fluid is highly flammable and can chemically deteriorate over time.
Let's zoom into Section 3, the heart, hydraulic pumps.
So, the crucial point to understand here is the difference between the two main families of pumps. On one side, we have non-positive displacement pumps, kind of like your standard centrifugal water pump. In these, fluid flow actually decreases as system resistance goes up. If you block the output, the flow just stops. But on the other side, we have positive displacement pumps. These are the absolute stars of industrial hydraulics. They stubbornly deliver a constant, fixed volume of fluid per revolution, totally independent of the system pressure. If you block their output, the pressure will skyrocket until the weakest component in the circuit physically breaks. No joke.
Let's actually look inside one of those positive displacement pumps. This is a vane pump. See how centrifugal force brilliantly throws those red vanes outward as the rotor spins? Those vanes track perfectly against the eccentric ring, trapping the fluid in expanding cavities at the inlet, and then literally squeezing it out at the outlet as the cavity gets smaller. It's highly efficient, and amazingly, this specific design can even run dry for short periods without failing.
Building on that mechanical ingenuity, check out the radial piston pump. Instead of sliding vanes, it uses actual pistons arranged like the spokes of a wheel, riding on an eccentric ring. As the central block rotates, the eccentricity mechanically forces the pistons to stroke in and out, drawing fluid in and just blasting it out. And because the parts inside are hydrostatically balanced, this pump can handle extreme, staggering pressures, up to 1,000 bar. That is an immense amount of force.
Moving right along to Section 4, Managing the Fluid.
Returning to our biological analogy, how do we protect the actual blood of our system? Well, the basic physics of the fluid matters deeply. For instance, as pressure increases, the fluid naturally becomes more dense and its kinematic viscosity goes up, meaning it gets thicker and flows slower through the tubes. Meanwhile, increasing the temperature does the exact opposite. It makes the fluid thinner. We also have to think about bulk modulus, which is basically the fluid's stiffness. Higher pressure makes the fluid stiffer and more responsive, but higher temperatures or trapped air bubbles, that makes it spongy and slow to react.
To manage all that fluid capacity and thermal expansion, especially under extreme aerospace conditions, engineers have to use highly specialized tanks. Take this aircraft reservoir, for example. It's actually pressurized by high-pressure bleed air tapped directly from the jet engines. By keeping a regulated blanket of air pressure, somewhere between 50 and 200 psi, right on top of the fluid, the system ensures the pump never starves for oil. This works even when the aircraft is pulling aggressive maneuvers or flying in zero-gravity conditions.
Okay, let's dive into our final section, number 5, Hydraulics versus Pneumatics.
This table perfectly outlines the contrast between the two heavyweights of fluid power. Hydraulics rely on relatively incompressible liquids. That gives us massive, stiff lifting power, but usually at slower speeds and with a higher degree of complexity. Pneumatics, on the other hand, use readily compressible gases, typically just ambient compressed air. Now, because air is compressible, pneumatics can't lift those same massive loads. But what they lack in raw strength, they make up for with lightning-fast, highly reliable, and incredibly clean motion. That makes them the absolute go-to choice for things like factory packaging, robotics, and automated assembly lines.
In a pneumatic system, the air compressor is the heart. It draws in unlimited ambient air right from the room, physically compresses it, and stores it in a tank. But right after that compressor, you will almost always find an FRL. That stands for Filtration, Regulation, and Lubrication. This brilliant little unit meticulously strips out dust and humidity from the air, regulates the exact pressure, and then injects a microscopic mist of oil into the airstream. That keeps those rapid, air-driven tools completely lubricated and surviving under constant use.
As we wrap up this explainer, I want to leave you with this thought. Fluid power is everywhere, quietly making modern civilization possible. From the hydraulic brakes that safely stop your car, to the pneumatic systems opening the doors on your commuter train, right up to the landing gear of your next commercial flight. So now that you know what to look for, where is fluid power secretly at work in your life today? Keep your eyes open and never stop learning.